in 2025, we'll be back in person in Sacramento for our conference, so stay informed. And we're really interested in looking at decarbonization of large commercial buildings here through a social science lens. And when I say social science, it's not looking at necessarily limited to individual decision-making, but also looking at organizations and communities and institutions. What goals are we setting? What codes and standards? What are the incentives that are needed to drive these changes? And we would love to, I'm just going to stop and say, we would love as much interaction on the chat as possible. So please feel free during the presentations to add your questions. We have a 90-minute session today, or 85-minute session today. For the first hour, each panelist will present, and we'll have maybe a minute for clarifying questions, but please, again, feel free to add those to the chat. And then we'll have about 10 minutes at the end for a longer Q&A. For the last 30 minutes, if you'd like to, we would love to encourage you to stay and join some breakout groups. We'll have 4 breakout groups, and the intention is just really to hear from you. What are the ideas you have about addressing these issues? So my name is Therese Peffer. I'm from CIE UC Berkeley. I'm the moderator. I've been the co-chair for BECC for a number of years. And with that, I'm going to introduce our first speaker and let him tee up his slides. So starting off is Paul Raftery, who's a professional researcher at the Center for the Built Environment at UC Berkeley. Paul has deep hands-on experience in a range of areas: heating, ventilation, air conditioning engineering, energy modeling, building automation systems and controls, fault detection and diagnostics, full-scale laboratory experiments, M&V, machine learning, software development. He's an active member of BECC and ASHRAE. And with that, I'm going to hand it over to you, Paul.
All right. So I'm Rupam Sangla. I'm an associate director at TRC. And what Paul is going to present is about 2 buildings which had huge energy savings potential, right? Therese already mentioned that we saw 70% gas savings in these 2 buildings. Paul will talk into the details of how we got to that, and he'll give some overall background on the research project. But basically, as part of that same research project, we wanted to understand how prevalent the sorts of issues that led to that huge savings, how prevalent those sorts of issues are, and how much energy is currently being wasted in commercial buildings, so that we can understand the savings opportunity and hopefully even understand what we can do about it. So we wanted to analyze more buildings, but there's really not a lot of data on heating hot water systems. So what Paul's going to focus on is heating hot water systems in building. This is where you have maybe a boiler with hot water piped around the building that's being used for space heating as part of your HVAC system. So there's actually not a lot of data in the public domain about how these hot water systems operated. So in order to understand the challenges with this system and understand how widespread these savings opportunities are, we had to first create our own data set. And to create our own data set, we reached out to hundreds of our own contacts nationwide, asking for heating hot water system data. So we were looking at data points including gas usage, hot water load, water flow rates, water temperatures, et cetera. And through our own contacts with designers, contractors, building operators, building owners, we collected data from thousands of buildings. So we had data from thousands of buildings. Unfortunately, a lot of it was really bad data. So we sorted through all the data, filtered out for where the data was good, where all the values looked reasonable. And we were looking for buildings where we had at least 1 year of data and where the data was hourly or sub-hourly, ideally 5-minute or 15-minute increments. So we weren't interested in, for example, like gas data that was just like monthly billing gas data, right? We really wanted hourly or sub-hourly data. So after all that filtering, we ended up with 259 buildings worth of data. So 259 buildings of good data from 56 different organizations. And just to give a snapshot of what those 259 buildings, what they looked like, you can see from these figures here that we had a range of building ages, a range of building floor areas. In the bottom left there, we have a figure showing the ASHRAE climate zone. So we had buildings we had a large number of buildings in California, but we also had buildings across the country. And then just a brief snapshot on the building type. We had a lot of office buildings, a lot of medical office buildings, some lab buildings, and then the colors here indicate the heating hot water system type. So whether there are non-condensing boilers or condensing boilers, district hot water or district steam. So that's just an overview of the buildings in the data set. So we analyzed all the data that we had, and we came up with a number of findings. And a lot of the findings were surprising even to us researchers. So today I'm just going to focus on 2 of those findings. And the first of those findings is that heating hot water systems operate far more than expected. So this histogram shows the fraction of hours spent operating for the buildings in the data set. Out of the 259 buildings, about half the buildings in the dataset operate more than 80% of the time. So for context, if you had a building that was operating, say, Monday through Friday, 6 a.m. to 6 p.m. year-round, including summer, that building would only be operating for 36% of hours. But here we saw that over half the buildings operated 80% of the time. So in most cases, these buildings are operating almost continuously, right? They're operating without switching off at night or on weekends or during the summer. So what we see is that there's a clear lack of understanding of the scale of the negative energy implications, cost implications, maintenance implications, and these buildings are just allowed to run almost continuously. So we have a few reasons why these systems may be operating excessively, right? So one reason is that the system may have poorly configured or implemented controls. Another reason may be because of concerns from a building operator that maybe a building operator is concerned about potential leaks from pipe fittings if they allow the system to cool off. I'll talk about this one a little bit more a little later. And then it could also, these systems could be operating nearly 24/7, really just due to lack of attention. So these hot water systems often don't get the attention that they require. So there may be a lack of awareness that the hot water plants are even running when they don't need to be. Or maybe a building operator manually set the system to run over a weekend, say for a special event in the building, and then that system was never returned to its original control, and then it just continued to operate 24/7 after that. Our next finding is around hot water supply temperature. So this figure that I'm showing, it shows what we expect to see regarding hot water supply temperature. So what we see is that when it's cold outside, the hot water supply temperature is relatively high. It's around 160 degrees. And then as the weather outside air heats up, as the conditions get warmer, the supply water temperature decreases and gets to a minimum of about 120 degrees. So heating hot water systems generally operate much more efficiently at lower hot water supply temperatures. So we only want the water to be as hot as is needed to meet heating requirements. So because at lower supply water temperatures, we have less distribution losses, and heating equipment tends to operate more efficiently at the lower supply water temperatures. So what I'm showing here is a system that's very well controlled. This only, out of all the 259 buildings in our data set, only about a quarter of them showed any sort of consistent correlation between the supply water temperature and the outdoor air temperature. Most buildings, that meant the other 3/4 of the buildings, generally had very poor control over the hot water supply temperature. So I'm just going to give a snapshot, just a few examples of what some of those other buildings looked like. This was something that we saw quite a bit, where it was just a constant set point. So this is actually 5 years worth of data. And you can see here that across all the outside air temperatures, across all the 5 years, that supply water temperature is around 170 the entire time. This is another example. This is an example of an inconsistent fixed temperature set point. So in this case, it looks like the set point is actually manually controlled. So it's clear that there were actually several different set points throughout this 5-year period. So it's likely that the set point was manually changed several times. Like maybe the set point was manually increased upon a perceived need for heating, and then maybe some warmer weather came, and then it was manually decreased for the warm weather. But then each time the change was made, that change stuck around for quite a while before it was manually changed again. And then this last example that I'm going to give is one where it looked like there used to be good control, and there was some correlation between the supply temperature and outdoor air temperature, but at some point the set point was overridden to looks like 150 or so. And since then, that's the temperature's just been stuck at that. So there are some common myths across the industry that are driving some of these findings. Both of the findings that I shared have a huge impact on energy use, and for the most part, it would be a low cost or a no cost fix to actually improve that. But part of the reason why these issues persist is because of some common myths in the industry. So I'm just going to briefly touch on some of what these common myths are that may be contributing to our two major findings. The first is that setting a higher water temperature will solve any cold complaint, right? Building operators are responsible for responding to comfort complaints, including complaints about being too cold. So they may think that the best thing to do to satisfy that cold complaint is to set the water temperature higher. Another myth is that you have to run the system, the hot water system, 24/7 in order to avoid leaks. This is a pretty prevalent thought among many building operators, and this may be a valid concern in some older buildings, but not all older buildings. It would just be for some older buildings, and it's certainly not an issue for buildings built within the last 20 years. But this myth seems to persist because maybe if an operator had an issue once with leaking valves, then they may forever after that conservatively operate the building in order to avoid that issue. And then they may even pass that myth along to operators that come after them. And then the last myth here is just that, and this is something that we've heard, that running the hot water system when the air handlers are off doesn't waste energy because the hot water system is insulated. So lastly, I wanted to, I mentioned the role of the building operator just a minute ago. I just wanted to touch on some challenges specific to building operators. So building operators are the ones that are ultimately responsible for the system operation that we saw, right? And some of the myths that we just talked about may be perpetuated among building operators. But they're often responsible for buildings that are already running poorly before they even come into the picture. And then the building operator is tasked with maintaining the equipment, maintaining occupant comfort, and running the equipment efficiently. So building operators face a number of challenges. And the first one is that operators are often stretched thin and have many demands on their time. This is true, I would say, of a lot of people and a lot of building operators across the industry, across different building types. The second challenge is that building operators are not sufficiently trained. So Peter's actually going to talk about this one a little bit later. But building operators are often not trained sufficiently to know that when there is a problem, how they can fix the underlying issue, right? So oftentimes the easiest thing for them to do, the most expedient thing for them to do is to override a set point or do some sort of other manual control. And that's really what, how we end up seeing those, for example, the supply water temperatures being much higher than they needed to be, right? That may have been an operator thinking that would be the easiest way to address an issue. And then the last two challenges I have here are really tied together. So building operators are incentivized to avoid problems, right? They want to avoid occupant complaints, they want to avoid leaks, avoid any disruption, but they're not incentivized at all to save energy. Oftentimes building operators are not tracking how much the energy is using, right? And the person paying the utility bill, the person who's seeing how much energy the building is consuming, like that person is likely in a completely different department and doesn't have any interaction with the building operator. So what we find is that building operators operate buildings to avoid complaints and not to optimize on energy use. So next up, Peter's going to talk about how we can train workers and see behavior change and organizational change and ultimately reduce energy consumption. But before I pass it to Peter, I'm not sure if we have time for questions now or if Peter's going to go right away.
Thanks, Rupam. I think we're going to see if Paul can come back on and
second time. It's our fourth time lucky. Let's give it a shot.
all right. Yeah. Go ahead.
Full
Paul.
restart there. We'll see. Hopefully everyone have their fingers crossed here. Okay, no errors. I don't know what a full restart seemed to have solved this. Well, sorry about that, and sorry for dumping you in. And it's early there, Rupam. Well, I got a Zoom quit unexpectedly, Therese. I have to switch over. Yeah.
Okay.
Or maybe Carlos, could I hop into you?
Okay, why don't we go with Paul, if you can, let's see, I have your slides up. So if you can talk over these, I can move them forward. Can you see those? Paul?
Can try this way if you want. I was going to hop into Carlos's office, but this is fine.
Oh, okay.
Yeah, okay.
Yeah.
So sorry about all the back and forth here, folks. I have no idea why this is crashing. That's never happened before. But Rupam has just walked through kind of a large data set showing that there are lots of issues in how these systems are operating in practice. And the plan was I was going to show you how we can save a large amount in 2 example buildings and lead into that, but we're going to do it a little bit backwards, I guess. So my name is Paul Raftery. I'm a staff researcher at the Center for the Built Environment. And today I'm going to be focusing in on how we can reduce emissions in existing buildings and proving that that's possible to do at fairly large scale and with a large impact. So you can go to the next slide there, Therese. No, actually, I think I can control it directly, I think. Perfect. Yeah, so just a little bit about our research group. We're what's called an industry university collaborative researcher center. We've been around just under about 30 years, and we're sponsored collectively by about 50 different partners. So they fund the research as well as state and federal research grants. So it's a really broad mix of folks. Actually, I don't think you've given me control there, Therese. Yeah, it's a really broad mix of partners, everything from manufacturers focusing on the built environment to big portfolio owners, as well as AUC design firms. And collectively, those folks give us insights into the problems the industry is facing and they're facing, and then we can do research to try and address some of those questions or issues they're facing. So looks like that's not working either. Wow, we're cursed. And the project that I wanted to talk to you about specifically here is one that we just completed this year, funded by the California Energy Commission. And this was focusing in on existing large buildings and trying to reduce gas consumption in those buildings. So really focused in on the site combustion emissions from the natural gas system. And in most large commercial buildings, that is for space heating, not necessarily hot water. The vast majority of gas use in large commercial buildings is for space heating. And this project was a really broad project. It involved measurements of these systems both in the lab and the field. You just saw Rupam talk about the data we gathered from hundreds of these buildings nationwide. And then I'm going to zoom in on the demonstrating reductions in existing office buildings. So this last point here. So next slide. Therese. Is Therese frozen now? Wow, this is like a comedy of errors here. And it's funny because we practiced it just beforehand. Um, well, Therese, her whole computer is frozen. Wow. Okay. Let's try. I can't. I've lost all control of this. So, is there anyone who's a host who can share screen? Or Carlos, are you a host?
Hey, folks. I think I'm just going to jump in here. My name is Ruben Sussman. I direct the BECC conference. And Paul, I'm sorry that you've had so many technical difficulties. It's really an unusual
So,
situation.
I know I've never had this before. I'm going to
I've made
pop
it in
into
the
my
past.
colleague's office, who is right there, and
Yeah.
that's Carlos. So if you can make him host, we can try this again another way, and
You know
we'll
what?
give that a shot.
Let's go to Peter for a
Or
moment
try
here.
Peter.
Peter, if you could set up your slides, and um, Paul, in the meantime, feel free to jump over to another computer and we can try you
Sounds good.
again. Peter, do you
All right.
think are you ready to go by any chance?
Sure. I'll give it a go.
Thanks, Peter.
Now, can you see my slide?
It's looking great.
Okay. All right, we'll give this a try. So I am Peter Crabtree, a visiting project scientist in CIEE at UC Berkeley, and I'm also the PI of the BEST Center. I'm going to be focusing on the workforce side of the picture. I think Rupan alluded to it several times, and so it was a good lead in to me. And thinking about the skills that are actually needed and how they can be applied on the operations side. And how big is this gap and how do we close it? Let's see. Oh, let me go over here. Okay. So just a quick couple of notes about the BEST Center. We are a National Science Foundation funded center through their Advanced Technological Education program. We partner with community colleges and technical colleges across the country. We also work with controls manufacturers, industry associations such as IFMA, labor unions and their apprenticeship training programs, national laboratories, especially our own LBNNL, government agencies, and others. And as I said, we're based at Berkeley. Previously, we were based at Laney College in Oakland, California for 9 years. And prior to that, we had 2 other National Science Foundation project grants in which we continued this work on building science. And by the way, you can find us at bestcenter.org. This is an image of the national network that we have. We work with colleges across the country, as you can see. Wanted to mention some commercial building trends that are important for this discussion. They are viewed as an important target of opportunity for GHG emissions reductions, as we know. There's an increased emphasis on health and safety, and there's been some focus on the links between productivity and environmental quality, although those links are not talked about that much. JLL, for example, has done a little work on this, and we've seen some other research, but it's a lot of research could be done, which could incentivize more emphasis on environmental quality and its importance from the standpoint of productivity. Across the country, we're seeing states, especially Washington, California, Massachusetts, New York, and cities such as Denver adopting building performance standards, which are creating new demands on the operations side of the house for benchmarking, carbon accounting, and other measures. And so This is putting a new kind of dimension on building operations. Easy energy efficiency improvement strategies, for example, lighting upgrades, have already occurred, and they have given way to more costly equipment upgrades or control sequences, strategies, which potentially are much more costly. There's also a growing focus in the sector on electricity demand management in states like California, which have very large renewable, i.e. variable energy production, and as that enters the grid, it magnifies peak load situations, and there's a need for, on the operations side, to manage energy in that sense. Finally, there's, we hope, an increasing awareness of the need for building operators to use new applications and technologies to implement energy efficiency and energy management strategies. And really, building operations is central to all of these trends. So this is kind of a proposition to the group here, because buildings are designed, engineered from above. There is an assumption that they are already target for energy efficiency. But the lessons from building operations, i.e. management of building systems from the bottom up, might suggest otherwise unless certain conditions are met. And we'll talk about that a little more. I think it's important to recognize that commercial buildings are legacy industries, both construction and operations, governed by traditional organizational structures. The transition from construction to operations is also fraught. Is there a complete set of documents? Are building controls fully commissioned? Are operations staff fully trained on equipment and control systems? And probably we can say with quite a great deal of certainty that no, they are not. On the operations side, tribal knowledge is so important to keep the building running, but it may also impede changes needed to obtain higher performance because, as I think Rupen was pointing out, knowledge is passed on from one to the next, and so it tends to perpetuate doing things the same as we've been doing them. Finally, cognitive knowledge and skills required for performance improvements are primarily in the cognitive domain. They're not replacing a boiler, turning a wrench. They are thinking skills, application of the BAS system to problem solving, analysis of data, interpretation of information, root cause analysis. These are all things that it's harder to do in a sort of OJT or on-the-job training environment. Operators need to be able to do these things, to spot the anomalies, to ask the questions. What, we did this override 3 years ago. Why are we still operating the boiler 24/7? If no one's looking, then nothing is done. This graphic kind of illustrates this, what we call the high performance operator skills gap. And if you'll notice that the y-axis kind of just runs out there with those baseline skills. So it doesn't matter if I've been on the job 10 years, 15 years, or 30 years. If nothing changes in my skill set, I'm still going to stay at that baseline skill level. Something needs to be done to move me up to high performance. Well known that there was sort of this deficit for operators. This is quoting from the ASHRAE guide, the Green Guide from 2010. And if operators do not understand features or sequences, they will tend to override them or disable them. And it is critical, these authors note, that operator training be conducted in a timely manner, and even that the owner's project specifications should document the amount of operator training and skills needed. Have we done any of this? I think there's real doubt about that. And there's this kind of gap between the design engineering community and then what happens in operations. And Steve Taylor really captured this from a control standpoint. And as he writes, programmable controllers can be programmed to do almost anything, including high performance sequences, but they seldom are, due to poor sequences written by the engineer, poor programming by the contractor, market pressures, and he doesn't specify what those are, but we can imagine that they are the pressure to get the job done quickly, poor commissioning, if any, and so we don't really know if the equipment is working as it was specified or that the control systems are working as they were designed. And of course, lastly, poor training of the building engineer. And what I like about this, Steve Taylor's perspective here, is that he's not pointing the finger at the operators or anyone in particular. He's looking at the whole train of events leading from construction to operations. I think I'm running short of time, so I'm going to have to move more quickly. But we can think of this, we can think of a building as conceived as being design engineered from the top down as a complicated system, but one which is predictable and replicable, and component failures can be located and corrected. However, on the flip side, buildings are operated from the bottom up as complex systems, more akin to a biological or social system. Human activity itself is crucial to how the system behaves. And this is kind of the fundamental issue that we're trying to get at here. And building operators have to make the building work. And so they do, through overrides, workarounds, whatever it takes. Some of the organizational challenges in achieving goals, the need for training of operators goes largely unrecognized. It's neither provided nor incentivized. There is a widespread mischaracterization of building operators as traditional non-STEM blue-collar workers, wrench turners, who don't use their cognitive abilities. And this mischaracterization becomes a self-fulfilling prophecy for very average operational expectation and performance. Another issue is that energy costs are a small fraction of personnel costs for most organizations. Energy efficiency is not viewed as an organizational priority, high on the list. And finally, the way the organization operates, facilities are always a good place to cut the budget, and this kind of firefighting mode that creeps in, where we're just moving from crisis to crisis, cold calls, hot calls, whatever, displaces high performance goals and objectives. So we can really characterize the education and training challenge. The vertical axis here represents new technology, and the horizontal axis represents extensive progress expanding the application of existing technologies, and that's really where the problem lies. We need to be able to use the technology that it's already available. It's been available for decades, frankly. So there's no reason not to be using that technology. And fundamentally, it's a lack of training. Just very quickly, how do we analyze and how do we understand that training gap? One way is to use case studies similar to ethnographic research. We did this with the BECC Center early on, and we sent very senior people out to kind of walk around in what we viewed as high performance building operations, say a museum, which has high specs, a data center, a high-tech facility, a medical research center. And we documented how the organization operated in a high performance environment. ASHRAE Guideline 32, I think, if you go there, it also emphasizes the importance of organizational commitment to high performance. Owners, managers, and operators working in concert. Operators cannot solve these problems by themselves. They have to be supported from above to do it. One other approach to get at these skill sets is the job task analysis, where practitioners, people that are actually doing this work, map out required knowledge, skills, and attitudes. But the problem is that this approach assumes that there is an organizational commitment and organizational goal setting. This was the strategy that BEST used to develop the high performance building operations professional national certification, which really drills down and goes into all of the JTAs and the KSAs involved in high performance. Very quickly, that certification builds on a substantial body of research. It recognizes the need for building operators to have broad knowledge and cognitive skills. It promotes the urgent need to educate and train operators. And finally, it really emphasizes the critical importance of BAS systems, because it's the BAS system that opens up the data for the operator. And you can go to hpbop.org and take a look at that information. These are some of the needed cognitive knowledge and skill sets for high performance, ranging from kind of a system level understanding. System manuals is very important. The use of the building control system, understanding energy literacy and energy conservation is critical at the operations level, because if I don't understand that, nothing else really matters. Being able to understand and apply commissioning. And finally, within the affective domain, the application of continuous quality improvement. This was called out by in the JTA by the practitioners. This is just a quick snapshot of some of the things that you can do with the BAS system. You can look at alarms, you can look at logs, look for trends, correct trouble spots. You can identify overrides and figure out whether they're still needed or not and undo them. You can review the building occupant schedule and ask why you're heating the building 24/7 and why you're not following an occupancy schedule. These are very basic functions that the BAS system allows you to do. And so often it's not being done. Why? Because operators are not trained to do this. They are not trained on the BAS system itself. And so on. And this is we at BEST, we did a training of operators from the Bay Area recently. We started, we took them through energy literacy, energy conservation, and so forth. And we also did a lot of work on building automation systems, Here are a couple of guys setting up a controller, wiring it up, programming the controller. This is a shot of this group of building engineers, many of them chief engineers from high-rise buildings in the San Francisco Bay Area, and so forth. One of them commented back, "I wish I had gotten this training 17 years ago. It would have changed my entire career." So I will close there.
Great. Thank you so much, Peter. And we'll move quickly to Paul. And Paul, maybe you can tighten things up a little bit. We're going to try to continue to...
I can't share while Peter is still sharing. So,
and thanks people who are putting stuff into the chat. That's exactly what we want, is to keep the conversation moving there as well.
All right. What is this? The 5th time lucky? Hopefully this does not crash. Can you guys hear me okay?
Great. Yeah, go ahead, Paul.
Yeah, you can hear. Okay. So thanks for your patience, everyone. Never happened before, but you know, this is how it goes, I guess. So I gave a quick introduction to myself. What I really want to dive into now is the project that we worked on, which was funded by the California Energy Commission and really focused on reducing natural gas consumption in existing large buildings. And the scope was pretty broad, but this presentation focuses on demonstrating reductions in existing buildings. So the 2 buildings that we worked on were 2 large office buildings here in the San Francisco Bay Area, both over 100,000 square feet and just under 20 years old. So in the context of existing buildings, they're not really that old, really. But they are definitely existing buildings. So you don't have the opportunities that you have in new construction to kind of trade off elements like, oh, we don't need to install a gas service, so it's a lot easier to electrify, or we can increase the insulation. You're kind of stuck with what you got, right? So in these buildings, looking at the HVAC system, the buildings when we started out had one oversized non-condensing boiler, very typical in this area. There was a campus or distributed chilled water system, and then there's 2 air handlers serving about 200 VAV zones in the building, most of which had hot water reheat. And we came into this project at the beginning. This is about in 2019, when the owner wanted to replace the existing boilers, kind of reaching end of life, and have some new, to have some redundancy there as well. And what we did is we layered on this CEC-funded research project to really try and maximize the possible efficiency gains through controls and equipment replacement in this building. So what we did at a very high level is we installed very aggressively sized, small, new high turn down boilers. So boilers that can operate all the way from 100% capacity down to 5%. And then the key element here is that we also did a full controls upgrade as well. Without replacing the actual physical controller hardware, we updated all of the control sequences and really tuned the building to operate well. And this is much more in-depth than a typical kind of retro commissioning exercise. We worked from the individual zone level all the way up to the air handlers and the boiler plant. And that part is key because all of those savings don't just add together, they kind of multiply together, right? You save a few percentage at each zone. That makes all of the supplier temperature and other types of resets operate more efficiently. And if you want more information in detail about what we did and how we did it, there's lots more resources at the end of the slide, including a paper specifically on this demonstration project, and also a design guide to help folks replicate this, and screening methods to help you identify buildings that will be candidates for similar approaches that we used here. So what were the results? Here you're seeing on the y-axis the daily gas consumption. This is actually from the utility bill from PG&E. And on the x-axis, we're seeing the daily average outdoor temperature. The blue line is pre-retrofit and the yellow line is post-retrofit. And as you can see, there's a huge step change in energy consumption in these buildings. This corresponds to 71% measured annual natural gas savings. And that is all the site emissions, right? This is all of the combustion on site. So this is your scope 1 emissions, a 70% reduction from efficiency measures and boiler replacement, but done in an in-depth way. In the second building, we had very similar savings, 69% in that building. And we also had quite substantial electricity savings as well. These are a little bit harder to quantify because of the impact of the pandemic and the metering that we had in place. But we saw about 20 to 25% fan energy savings and about 40% chilled water savings in these buildings too. In total, the energy cost savings, just the utility bill savings, are over $100,000 a year in both of these buildings from these combined efficiency measures. They're so big that you can even see it on your monthly utility bill. These are the monthly utility bills for these two buildings going back over a decade. The blue line is the pre-retrofit average, and the kind of gray highlighted area in the background is the lowest and highest monthly bill they had in that whole 10-year period. And you can see that yellow line in the pre-retrofit is lower substantially than all of those without even accounting for differences in weather, right? So these are absolutely enormous emission savings that you can get from really in-depth efficiency measures. But of course, 70% is not 100%. How would we reduce the emissions even further in these buildings, right? Or if we could go back to 2019 and think about electrification at that particular time, we might have done it then, but right now we can analyze the data that we have and see how much further we could go. So if we were to reduce emissions even further in these buildings, we'd need to switch fuel sources to something that's cleaner, and that's electric power from the grid. And when you look at these sorts of studies, when you're trying to electrify heating, you always have a decision about how large the heat pump or the heating equipment should be to offset that boiler capacity, right? And I wanted to step through some of those issues here because that really is a key consideration. And there are some real world practical constraints that sometimes are quite challenging in existing buildings. So here, this is one of those office buildings that we talked about here. This is just a screenshot of the roof. The footprint of the new boilers is highlighted there in orange, right? And when you're looking at putting in a new heat pump, you have to consider things like the cost of the equipment. It's much more expensive. The physical space where you have to put it because it's much bigger. The weight, because it has to go outside, typically on a rooftop that wasn't necessarily designed for the additional weight. And of course, you need a larger electrical service capacity up there. And all of those things constrain the size, or at the very least, add step changes in cost for different sizes. So for some context here, this is the air-to-water heat pump if we were to fully electrify that building with exactly the same capacity as the boilers that we installed. So we also, in our analysis, wanted to assess a partial electrification case where you would keep the same boilers, but you would install a relatively small heat pump to try and operate that as efficiently as possible and offset as much of the gas use as we can, while still keeping the size of the equipment to the point where it would be more feasible to install. The heat pump we modeled in the partial electrification case is about 14% of the installed boiler capacity, which, because of the redundancy requirements in this plant, is about 20% of the peak load. And one of the things that's really interesting about heating loads is that they're very skewed distributions. And what I mean by that is most of the time, the building heating loads are quite low. They only very rarely approach the kind of peak heating temperatures, right? We have to design for the coldest day of the year or coldest day of even the building would ever reach, but it's very rare we actually operate in that over the context of a whole year. What that translates to is that a really small heat pump can actually service quite a lot of the annual heating demand in a building. And we saw that in the larger data set that Rupam presented as well, if you want to look at that data in more detail. And the other thing you might want to consider, aside from how big of a heat pump you will put in, is when it operates, because the grid itself is much cleaner than burning gas on site, but it varies quite a lot what the emissions are on that grid, how much carbon dioxide is emitted to generate the electricity that's delivered to the buildings. And particularly in California, there are times when the grid is very clean, like in the middle of the day when there's excess solar on the grid. But there are also times when the marginal generator is actually a natural gas power plant. And what I mean by marginal generator is if you were to plug, your electric vehicle into the grid and start charging right now, what would be the generator on the grid that would ramp up production due to that increase in load? And this data is tracked by companies like WattTime, and we're seeing a snapshot of that here from this year in February. You can see there's a real big dip in the middle of the day when there's a lot of solar on the grid, and that's when electricity is super clean, right? Great time to use electricity, especially if you're switching from some other fuel. Now, if we layer on the actual measured building loads, the heating loads in these real buildings that we're talking about for this demonstration, you can see what that looks like here in red. And this is the heating load, or how much heat energy is needed to heat up your building. The red line is the actual gas boiler's output, right? If we were to fully electrify, we would service that with electricity instead of gas. When we have this partial electrification case, even on this relatively mild February day, we actually only able to offset a bit more than half of that load for over the course of the whole day. You can see that small little heat pump is maxed out even on a mild day, and the rest of the heating capacity has to be handled by the gas boilers in that case. But you might also notice that the time that these heating loads are happening also correspond with the time when there isn't any solar on the grid, right? It's early morning before the sun is up. So generally, you actually have higher emissions on the grid at that point in time. And you also have colder temperatures, so the equipment, which is an air source heat pump, is less efficient. And you have less capacity. So all of these factors combine together to reduce the actual emissions you're saving in that particular case on today's current grid. And this is both scope 1 emissions, so both site combustion emissions and the emissions associated with the grid. When you layer those three things together on this particular day, there isn't a huge difference between the savings from partial electrification and full electrification, right? At least on today's current grid. And when we look at an annual analysis, you'll see what that factors together, not just this one specific day, right? So stepping back again for a second, when you're thinking about existing building decarbonization and think about this project, we saw enormous emissions reductions from thorough energy efficiency measures, right? Not just a cursory controls check, but really going down into the weeds and spending time fixing every single issue from the zone up to the air handler. We were able to reduce the emissions associated with the heating system, the site combustion emissions, by 70% in this building. And doing that first, before electrifying, will actually make electrification easier because you're reducing hot water temperatures, you're reducing loads. It will put less stress on the grid after electrification. On today's current grid, if you were to partially or fully electrify those loads using an air source heat pump, you would definitely get additional emissions reductions there. But partial electrification would actually reduce emissions by almost the same as full electrification, but it would do so at a fraction of the cost and embodied carbon and refrigerant losses. And those heat pumps would actually operate at more uniform loads instead of potentially cycling, which happens when you have very large air source heat pumps being installed in several projects we've seen. Looking out further, say to California's commitment for a fully clean grid by 2045, even there, a partial electrification solution will get you to 95% of the reduction in carbon emissions compared to the pre-retrofit case. But again, the vast majority of those savings were from efficiency on the controls measures that we saw in these buildings. So I really want to drive that point home. If you take one thing away from my talk today, is that there's a lot more potential to reduce emissions through efficiency measures than people think. Right? We really need to do something similar for lighting that we did, replacing everything with LEDs and improving controls. We need to do something like that with HVAC systems. And we need to do that before electrifying, because the biggest emissions reductions we're going to get are by not wasting energy in the first place, rather than switching from one fuel source to electricity. If we didn't need to use any fuel at all because we were just wasting energy pointlessly, it's much better to fix that problem first, right? And I think the other key takeaway that I have, which was intended to lead into Rupam's and Peter's presentations, is that this is not the simplest stuff, right? It's a pretty complicated system, even to begin with, without looking at electrification. And expecting people who are operating these buildings day to day and doing 10 other tasks, or owners to be able to like just jump in and decarbonize their infrastructure without any training or incentives is not going to yield very positive outcomes. We really need to focus on building operators and decision makers in large organizations and provide them with the training and the resources to be able to tackle this problem. And a key part of that is time. If a building operator has zero time right now, and you try and layer on a large decarbonization project on there, they just won't be able to do it, and you won't have good outcomes. So for looking in at existing large buildings, the key things that you can do, aside from training and resourcing the operators, is make a plan for each building. They're all unique. They all have their own unique set of constraints. Think about the next 3, 10, 15 years, and think about what's going to happen over that time frame anyway. What equipment is going to need to be replaced? What types of renovations might happen? And understand the constraints that you're working with on that site. Is it a downtown high-rise? Well, if it is, chances are an air source heat pump up on the rooftop is not going to be an option for you. Are there structural constraints or electrical constraints? Having a good understanding of all of those will take time to understand and dig into, and it will take training to dig into. But knowing that in advance will allow you to make the most kind of synergistic decisions about electrifying and reducing emissions at these sites. Once you have that understanding, or as part of getting that understanding, it's absolutely critical we install HVAC metering. Most buildings have very little metering, if any, other than what the utility meter says. And if you don't even know what the heating loads are in your building, it's very difficult to accurately size replacement equipment and consider alternatives like partial electrification and the full set of emissions reduction that might be feasible with a strategy like that. The other step that we should be looking at doing at very large scale is these types of deep controls and efficiency measures, because these will be the most cost-effective carbon emissions that we will get anywhere, right? It will be way cheaper to reduce emissions, 1 ton of emissions through controls and efficiency work than it will be to do it through equipment replacement. The next thing you can also look at doing in buildings, once you've fixed these kind of controls issues and kind of eked out as much efficiency as you can, is run the buildings over the winter for a stress test. So this is where you lower things like water temperatures to see how the building operates with much lower water temperatures that are suitable for heat pumps, and where are the problematic areas of that building and what you can do about those, so that, you know, the one corner office isn't driving the water temperature for a 100,000 square foot building. It's better to fix the issue in that one corner office rather than just run at high water temperatures for the whole building. And this iterative process, which will take more than 1 year, will allow you to understand the building well and understand the constraints that you're facing. And at that point, that's the best point to electrify. You know your building well, you can have a plan for the future. You've already captured all of the efficiency gains, so you're not wasting energy. At that point, you electrify as much as possible to get that last set of emissions down to as close to zero as we can. So with that, I'll just close and say that, you know, this is a really large project. I didn't have time to go through my my first slide there, but there are a ton of people involved that I just like to thank. They're all listed there in that first slide. And we have a lot of resources from this on our website here at the QR code. That includes a design guide for kind of walking you through the process of what we did and replicating it in your own building, screening methods for identifying good candidate buildings for these types of retrofits, the data analysis from hundreds of buildings that Rupam presented a little while ago, and the results of this demonstration project. All of that is all available free to the public at this link here. So with that, I'll pass it back to Therese, and I think we'll hopefully make questions. To be honest, I'm just glad the slides didn't crash, but looking forward to taking your questions now that we've gotten through those without any more technical difficulties.
Yeah, unfortunately, Paul, I think we're going to have to move to the breakout session. So if you do
Okay.
have, Paul's email is there. If you have questions specifically to him, please
Sure.
send that. Paul, if you could unshare, and then I will share just the one slide I have that describes the our next role here, which is we want to hear from you. We want to hear what is it that you know, what is it that we can talk about? What are the things that we need to be looking at? Paul addressed, you know, the goal of full versus partial electrification. How do we ramp that down? A lot of goals out there right now are pretty binary. You know, cut off all natural gas. So let's talk about that. Let's talk about what are the incentives that people need, not just at the building operator or engineer level, but up who are making the decisions to send these folks for training, and can we call them building engineers instead of thinking of them as operators? So there's a cultural shift too that's needed. The role of AI, someone brought up. So you know, the role of building performance standards. So these are all the things we want to talk about in our breakout groups. So I hope you can join. We understand if you can't, but right now we're going to break into 4 different groups, and we'll have opportunity to hear from you.